For most of human history, the only light we knew came from the sky. By day, the sun. By night, an uncountable number of stars. Now, from the beginning, our ancestors believed that the sun and the stars were heavenly, out of this world, and they were right. We've been watching the sky for thousands of years, but until recently, we couldn't see well enough to understand our connection to the cosmos. But now, our astronomical vision has sharpened. We can see farther and clearer. We can observe objects that are invisible to human eyes. Our increasingly improving vision has allowed us to make great discoveries, revealing an astonishing and wonderful universe. What follows are 13 of the Our first great discovery happened over centuries as the first humans looked carefully at the sky in places like this, the empty, cloudless deserts of the American Southwest, the Middle East, Africa, and South America. Of these ancient astronomers, the most important were the Mesopotamians. They considered the objects in the sky gods and built giant towers so they could record the rising and setting of the sun, the moon, and the stars. For more than 1,000 years, they used clay tablets to record what they saw. To find out more, I paid a visit to Professor of Astronomy, Owen Gingrich.
Here, for example, is one of these clay tablets. Have a read.
Yeah, these people wrote small.
Yes. I was perfectly amazed when somebody came into my office and picked it up and actually started reading it.
So what language is this?
I think this is in Babylonian. Hundreds of these tablets were unburied. Among these hundreds of tablets is a tablet called the Venus Tablet of Amazadaga. And this tablet contains the motion of the planet Venus. That's the earliest record we have of a planet moving.
After the Mesopotamians made the first records, it was the Greeks who took the next step.
Some of the Greek astronomers made a field trip out to Mesopotamia to find out what had been going on there, and they seem to have brought back some systematic records, so that ultimately it gave the basis for making a mathematical theory of the motion of the planets.
From their observations, the Greeks developed a vision of the solar system that would stand for some 2,000 years. That the planets move, revolving around the Earth. It would take our next great discovery to set the record straight. The year is 1543. A 70-year-old man is dying. His name? Nicholas Copernicus. A doctor and lawyer by trade, but for nearly 40 years, he was also an amateur astronomer. A pursuit that had led him to challenge one of the most fundamental and sacred beliefs of his time. As a young man, Copernicus had studied the heavens and found that the Greeks' Earth-centered system failed when it came to predicting planetary motion. He began to wonder if the Earth itself moved.
But here is Copernicus's idea.
With the sun as the center.
The sun is the center, and now suddenly
all the planets
are going always the same way around. They're not stopping.
Copernicus realized that the movements of the planets were better explained if the sun were at the center of the solar system and the Earth circled it like an ordinary planet. It was a revolutionary insight.
Despite any evidence that the Earth was moving, he came up with this book, which gives his new theory.
This idea, this book, changed the world.
Yes, because it made the Earth a planet, and it fixed the sun in the center. If you don't have that blueprint, you don't march ahead to the physics of the cosmos as it happened. The final pages, which were just these here in the front of the book, came to him on the very day he died. I suspect, I mean, he was lying there partially paralyzed from a stroke. He was probably just hanging in there till he could make sure that it was done.
Everyone, from the Greeks to Copernicus, assumed the orbits of the planets had to be circular. But in 1571, German mathematician Johannes Kepler shattered that assumption with our next great discovery. Lacking calculus, Kepler improvised ways to compute the circular orbit of Mars. The work was tedious. Kepler wrote that he was almost driven to madness considering and calculating the matter. His calculations began to reveal that the accepted notion of planets moving in circles simply did not work. Then a new idea came to him.
Kepler realized somehow the sun had to be driving the planets in some way that he didn't fully understand, and to get a self-consistent picture, he found that an ellipse was the path rather than a circle.
With this breakthrough, Kepler had devised the first method for accurately predicting the movement of the planets and stars across the sky.
When his tables predicted the planet Mercury to pass across the front of the sun, and nobody else's tables were close, that was dramatic proof of the accuracy of his astronomy. It linked the motions of the planets solidly to the sun. This was a very important point to help stress the idea that the Copernican sun-centered system really had physical significance.
Despite the success of Kepler's theory, many remained skeptical that the sun could be the center of the solar system. But the final nail in that coffin was about to be driven home by a man who, like Kepler, preferred to use observational evidence to form his theories. And that man was Galileo Galilei. Meet Galileo Galilei, a man determined to pursue truth no matter where it led. And in the case of our next great discovery, his determination led him to revolutionize our knowledge of the solar system. The year is 1609, and Galileo is fascinated with a new invention called a telescope.
Essentially, it was a toy out of a carnival. When Galileo heard about it, he went to work making one. He perfected it and essentially converted a toy into a scientific instrument.
Galileo turned his telescope skyward and was the first to see the mountains on the moon and the star clusters of the Milky Way. Then an extraordinary sight. A group of 4 small bright stars arranged around the planet Jupiter.
We have the manuscript of his first week of observations, and it's wonderful because you see him gradually coming to the conclusion that these little stars are carried along with Jupiter.
This was the moment of discovery. Galileo realized that the stars were actually 4 moons orbiting Jupiter. He had the insight that these moving dots were orbiting a planet.
I sometimes say he invented the satellites, and you say, wait a minute, they were there, how could he have invented them? He invented the idea that they were going around the planet.
Here was proof that Copernicus was right about the structure of the solar system. If moons could orbit Jupiter, then the Earth could orbit the Sun. And Galileo's discovery demonstrated that knowledge in astronomy can only be advanced by actual observation. A theory can only be viable when it's supported by the facts, just like our next great discovery. For centuries, comets had been considered harbingers of evil. By the end of the Middle Ages, a comet's appearance invoked fear and terror. But Renaissance scientist Edmund Halley, like Galileo, was interested in facts, not superstition. In 1695, he began searching for records of ancient and recent comet sightings. He found 24 comets whose passage across the sky had been recorded with enough detail to allow him to roughly plot their orbits. To his surprise, he found that 3 of the comets seemed to follow the same approximate orbit, circling the Sun every 76 years.
On that basis, he figured, okay, this is a comet that's going to be back in another 76 years.
He figured out that the 3 comets were actually the same comet.
The same comet.
Halley was so certain of the comet's orbit that he made a bold prediction. He said the comet would return in the year 1758.
And guess what?
It was.
The comet came back.
Unfortunately, Halley was no longer alive to savor his discovery. Since then, Halley's Comet, as it's known, has been greeted 3 more times by excited skywatchers across the globe. No longer a harbinger of evil, Halley's Comet became a milestone discovery in the history of astronomy, replacing a superstitious belief with a rational scientific understanding of the physical universe. In the 18th century, William Herschel was a classically trained musician whose love of astronomy led him to give up music and turn his attention to the heavens, thus setting the stage for our next great discovery.
When he discovered the price of a refracting telescope, which was beyond his means, he decided to make his own, and he became the most fabulous and successful telescope builder of that period.
He used his telescopes to methodically survey the sky, cataloging what he saw.
As he was searching the sky, he came across an object that looked a little bit different. Turned out to be a new planet.
Oh, wow. And what planet was that?
That was the next planet beyond Saturn, the planet Uranus.
Uranus was the first new planet to be identified in more than 3,500 years. But finding a new planet was nothing compared to Herschel's larger goal. He built a powerful 20-foot telescope, then divided the sky into equal sections and began to systematically count the stars in each field. It was a painstaking, monumental task. Slowly, Herschel's star count began to reveal something extraordinary. The Milky Way was much larger than anyone knew. It was a gigantic disk of stars. Some of its fields were jam-packed. One showed more than 250,000 stars alone. Other fields, farther away, were practically empty. Herschel's discovery was a revelation. This is a reasonable model of the Milky Way as we know it now. But Herschel was only looking at an area about this big, is that right?
What Herschel was seeing was a small range like this, maybe that big. So it was really a small part of the entire Milky Way.
But even that small part significantly changed the study of astronomy. Herschel's discovery revealed that our solar system was just an island in a deep and expansive universe. Thanks to the musings of an obscure clerk working in the Swiss patent office, our next great discovery revealed that the universe is a strange, mysterious place. That clerk was Albert Einstein. In the early 1900s, he was puzzled, along with the rest of the scientific community, by the orbit of the planet Mercury. Despite the ability of Newton's laws of gravity to precisely predict the motion of the planets, the laws failed when it came to correctly predicting Mercury's orbit. The puzzle had to do with Mercury's perihelion, that point in its orbit where it's closest to the Sun. Every century, Mercury's perihelion advanced slightly, a change that Newton's equations could not account for. In a bold and startling move, young Einstein proposed his own theory to explain the puzzle of Mercury's orbit, and in the process, developed a theory that refined Newton's laws of gravity. Michio Kaku is the theoretical physicist at the City University of New York.
Newton says that gravity travels instantaneously throughout space, and that's where Einstein thought there was a weakness in Newton's theory. He wanted a theory that could explain gravity. He wanted a theory that could explain acceleration and zigzag and circular motion. There has to be waves, gravity waves. It takes time for gravity to work its magic.
To propagate.
To propagate. So if the sun were to disappear, it would take 8 minutes for us to know about that fact. Even gravity travels at the speed of light. Einstein needed a new picture to explain that. And that picture was curved space, that space itself has curved, and that's why objects move.
Einstein believed that his concept of curved space was responsible for shifting Mercury's orbit. Einstein called his idea the theory of general relativity.
Imagine a trampoline net and place a bowling ball in the middle of a trampoline net. The bowling ball sinks into the trampoline net, and now shoot a marble around the trampoline net. The marble will orbit around the bowling ball. Now, from a distance looking down, Newton would say that there is a force, an instantaneous, invisible force pulling the marble down to the bowling ball. But Einstein would say, there's no force. There's no pull, it's just a trampoline net. And why is the marble orbiting around the bowling ball? Because a trampoline net is pushing the marble. Therefore, why am I sitting on this chair? Not because gravity pulls you to the ground, it's because space pushes me down toward the planet Earth.
The idea that space itself was warped by mass was too strange for many to accept. An approaching solar eclipse gave scientists the perfect opportunity to put Einstein's new theory to the test. Photographs were taken of the background stars before the eclipse and then afterwards. These pictures were then compared with photos taken during the eclipse. The photos showed that the positions of the stars in the eclipse photo shifted slightly inward, bending as the light from the stars passed the sun's gravitational field. Einstein's theory of general relativity was right. His great discovery rocked the world.
General relativity strikes a deep emotional chord in anyone who's ever looked at these equations. These equations are 1 inch long, and yet they answer these eternal questions that have dogged us ever since we first looked in the night sky and asked ourselves the question, what's it all mean?
General relativity had shown that space was weirder than anyone could imagine. Anyone but Einstein, that is.
To gain a clearer understanding of this strange universe, astronomers needed more observational data. And that required larger, more powerful telescopes, like the one that led to our next great discovery. When the Herschels had finished their survey of the heavens in the 1830s, they had cataloged thousands of these beautiful but hazy objects, then called white nebulae. At the time, no one knew whether they were part of our galaxy or distant island universes like the Milky Way. In 1924, astronomer Edwin Hubble was studying the stars in several of these nebulae using a 100-inch reflector telescope at the Mount Wilson Observatory in California. The telescope enabled Hubble to estimate that the galaxies were routinely many hundreds of thousands, even millions of light years away. Here were objects as huge and as populated with stars as our very own Milky Way galaxy, which is why we today call white nebulae galaxies. The more Hubble studied these galaxies, the more he became intrigued. At the time, scientists knew that a beam of light from a star appears as a different color on the spectrum. The color changed according to the motion of the star. A shift toward the blue end of the spectrum meant the star was moving closer to Earth. A red shift meant it was moving away. The amount of the color shift also revealed the speed of that movement. Hubble found that when he measured the distance of a galaxy, its spectrum almost always was shifting to the red. And something else. The farther the distance, the greater the red shift. In other words, the universe was expanding. It was an astonishing discovery with profound implications. Measuring backwards from the expansion, scientists found that the universe appeared to have a cataclysmic beginning, what one astronomer labeled the Big Bang.
Just 3 years after Hubble discovered the expanding universe, our next great discovery revealed a mysterious object hidden behind the dust at the center of the Milky Way and gave birth to a whole new branch of astronomy using wavelengths invisible to the human eye.
In 1930, Carl Jansky was a 25-year-old physicist working for the Bell Laboratories in Holmdel, New Jersey. Jansky's job was to identify the kinds of interference occurring at the 15-meter wavelength, then used for ship-to-shore and transatlantic communication. After spending more than a year recording data, Jansky decided there were 3 forms of static at this frequency. The first was clearly produced in the Earth's ionosphere. The second was caused by local thunderstorms. And the third signal was mysterious, continuous. It was coming from what appeared at first to be the sun. Each morning, this signal slowly rose with the sun. During the day, it rotated across the sky. And then, it set when the sun did. But as time passed, Jansky found that the mysterious radio signal slowly drifted away from the sun, as if it were coming from a point outside the solar system. Eventually, Jansky pinpointed its location as somewhere in the region of the constellation Sagittarius. He believed he had discovered an unknown interstellar object at the center of the galaxy. And he was right. Later astronomers confirmed that Jansky had discovered a supermassive black hole, equal in mass to 3 million suns. Perhaps even more significant, he was the first human to look at the universe using radio astronomy, a whole new way to study the sky. It was a landmark discovery, Jansky had proved that the sky does not merely sparkle with the gentle glow of starlight. Hidden out there are many strange objects, many light years away, that actually radiate more energy than whole galaxies, like quasars and pulsars, dead stars spinning madly with masses so dense that a single teaspoon would weigh millions of tons.
Before astronomers could even begin to understand the life and death of stars, new telescopes would have to be built that could look at the sky in many different wavelengths. Before that could happen, though, radio astronomy produced another great discovery that, although predicted, was as unexpected by its discoverers as Jansky had been. And once again, it happened at Bell Labs in Holmdel, New Jersey.
In 1964, Bell Labs had this spare 20-foot microwave antenna sitting dormant. Rather than destroy it, the lab decided to let astronomers use it for research. Two physicists, 31-year-old Arno Penzias and 28-year-old Robert Wilson, decided to use the antenna for measuring the temperature of the gas halo surrounding the Milky Way galaxy. What happened next is one of the most exciting discoveries in modern astronomy.
Hi, Bill.
Dr. Wilson.
And I came to Bell Labs to get the story firsthand from Robert Wilson himself.
Two of us, Arno Penzias and I, had just come to Bell Labs from graduate school, and we were going to measure radiation from the Milky Way. And that's where this antenna really fit in, because we could reject the radiation from the Earth, and what was left is what's coming from the sky. We were only getting about 2 degrees from the Earth's atmosphere. Maybe pick up 1 degree from the walls of this thing. But when we first turned it on, it was about twice that. It was 7 degrees. And this just wasn't right. Something from the Earth must be in our instrumentation. We, of course, are on a hill here that overlooks New York City. We had the ideal instrument for checking on that, though. We merely turn it down to the horizon, scan the horizon, and lo and behold, nothing particular extra. There was a pair of pigeons that lived in here, and of course it was covered with white pigeon droppings. So we thought, well, maybe the pigeon droppings are doing more than we think. Arno and I got up in here and we cleaned all the pigeon droppings out. Got rid of the pigeons.
What happened? How'd you get rid of the pigeons?
Well, first we put them in the company mail and sent them as far as we could, which was Whippany, New Jersey, to a pigeon fancier there who said, these are junk pigeons, and let them go. A couple of days later, they were back.
40 miles away, they came back.
Yes. So then our technician brought in a shotgun.
And then how did that work?
Well, I wasn't here, I didn't see it, but basically it didn't solve our problem. We still had an extra 3-4 degrees. We were really beginning to be perplexed because, we believe in physics. Mm-hmm. It's coming from somewhere. We can calculate what the horn is doing except for this excess noise.
At the time that Penzias and Wilson detected the radio static, there were two competing theories about the origin of the universe. There was the Big Bang theory, which Hubble's expanding universe supported. And there was the steady state theory, which proposed that the universe is timeless, with no beginning or end, expanding forever. When a friend heard what Penzias and Wilson had found, he suggested they get in touch with some cosmologists at Princeton University who were advocates of the Big Bang theory. They believed that a Big Bang would have left a faint thermal afterglow in the universe, traces of heat from the roar of the bang itself, detectable across the entire sky. And they were about to conduct research in hopes of measuring that afterglow.
We invited them over. They came over and looked at what we had done and immediately agreed that we had measured what they were setting out to do.
So what did your discovery mean?
Well, it means that we live in a Big Bang universe and that we're seeing the radiation from 300,000 years after the Big Bang. In many cases, when there's a paradigm shift in science, it takes a generation before people really accept it. But in this case, I think the world was ready for it. Human societies have always worried about where they came from. There are religious stories in every civilization that's ever been found. And I think we have a definitive answer, that we came out of a Big Bang.
The coming of the space age ushered in a golden age of astronomy that is still going on today. That golden age began, strangely enough, not in space, but with a turning point in Cold War relations that also contributed to our next great discovery. In the 1960s, despite a nuclear test ban treaty, the Soviet Union refused to allow on-site inspectors at its nuclear facilities. As a result, the U.S. opted to monitor the Soviets by developing an orbital satellite system capable of detecting gamma-ray bursts produced by nuclear explosions. Because the satellite's detectors looked up as well as down, scientists decided to use them to see if supernovae produced gamma rays when they exploded. Between 1969 and 1972, they detected evidence of 16 short gamma-ray bursts scattered across the sky. There was just one problem. None of the bursts correlated with any of the known supernova events. And the mystery deepened. Over the next 2 decades, astronomers detected an average of 1 gamma-ray burst a day. But each burst happened so quickly that it was over before astronomers could get a telescope aimed at it. Finally, astronomers began to solve the puzzle with the help of the Beppo-Sachs Space Telescope, which was designed specifically to detect short bursts of gamma and X-rays and precisely pinpoint their locations. On December 14, 1997, Beppo-Sachs located a gamma-ray burst, leading to the first photographs ever taken of a burst in wavelengths other than gamma. To their astonishment, astronomers discovered that the burst took place in a galaxy 12 billion light-years away, making it one of the universe's most powerful explosions. Since then, dozens of other gamma-ray bursts have been similarly documented, all just as powerful and far away. As for what it all means, the discovery of gamma-ray bursts have once again shown us that hidden out there behind the veil of the Earth's atmosphere are objects that are not only strange and hard to fathom, black holes, pulsars, quasars, but they're lethal too. Gamma-ray bursts are now considered a possible cause of past extinction events on Earth. The scientist Sir Arthur Eddington once noted, "Not only is the universe stranger than we imagine, it is stranger than we can imagine." He could have been talking about gamma-ray bursts, the expanding universe, or the theory of general relativity. It also happens to be a perfect description of our next discovery. Once it would have been impossible for astronomers to imagine discovering other solar systems with planets like our own. But today, astronomers can imagine thanks to powerful space and ground-based telescopes, like the one here at the Lick Observatory in Mount Hamilton, California, where Jeff Marcy is hunting for new planets. How do you go about finding a planet around a star?
Well, it's very easy. We watch the star to see if it wobbles in response to the planet, yanking on it gravitationally.
Very easy.
Very easy.
Oh, you just need one of these.
That's right. This is the 3-meter Lick Observatory telescope. By definition, planets don't produce their own energy. They shine, of course, by reflected light, but planets are about 1/1000th as bright as their host star, so you can't really see them, even with the Hubble. You need a trick, and that's what we use with this telescope.
A trick.
The Doppler effect is our trick. We measure the wobble of a star by the changing light waves that come from the star as the star wobbles.
The search for extraterrestrial planetary systems gained momentum in the early 1990s when a Polish astronomer made a surprising discovery.
There's a wonderful discovery by Alex Volchan of a system of 3 planets orbiting a pulsar, and the way he found them was quite exciting. He watches the pulses coming from the pulsar, and the arrival of those pulses changes as the pulsar approaches and recedes us. These are hideous stars. Pulsars have ultraviolet X-rays and gamma rays coming off them. They're the bizarre end products of a supernova explosion, and despite that bizarre environment, here we have Earth-sized planets going around it. If there are Earth-sized planets around pulsars, you can bet there are Earth-sized planets around other stars.
There are Earth-sized planets around pulsars?
Earth-sized and even moon-sized among the 3.
He
Yes.
detected those.
Detected them by this wobble of the pulsar.
Well, that's just the coolest thing in
It's
the world.
unbelievable.
Since Volchan's discovery, Marcy and other astronomers have found more than 130 extrasolar planets.
We thought we would never find even one planet, and we have found the world's only triple planet system and quadruple planet system with this telescope.
Oh my! So these are big planets, though.
These are planets the size of our Jupiter, Saturn, and the smallest are Neptune-sized.
Yeah, little Neptune.
So it's quite exciting. We're finding planets of Jupiter size, but even those a few times bigger than the Earth.
While no Earth-like planets have yet been found, the search continues.
How do you pick a star as a candidate?
We indeed try to choose stars that are more or less like our sun, some more massive, some less massive, but sort of middle-aged or older, so they've settled down. What you want from an Earth-like planet to make it habitable is the temperature has to be just right. Not so cold that the water's locked up into ice, not so hot that the water's evaporated into steam, but a planet just the right distance from its star so that the temperature is just right for liquid water over billions of years to let Darwinian evolution do its thing.
Sounds like Goldilocks and her porridge.
That's right. You don't want it to be too hot or too cold.
Suppose you had a telescope, a gizmo, a device, sensitive enough to find an Earth-like planet. Would you point it at some of the stars you've already identified as having planets?
Absolutely. The Jupiters and the Saturns we're finding are the signposts, the benchmarks of systems that might harbor Earths, and especially if there's a Jupiter far enough from the host star, that leaves room for an Earth in the habitable zone to be orbiting that star.
What made you go looking for planets on other stars?
Well, I remember when I was a young kid, I thought to myself, I wonder if there are other Earths out there, and if so, are any of them habitable? And then, is there life on those planets, and in particular, intelligent life? We humans, I think, in general, would love to know, are we alone in the universe? Are there other planets like Earth, habitable planets? Are there other creatures out there that think and dream and indeed are searching for us? In the end, I think we humans are trying to find our roots out there, chemically and biologically, among the stars.
As the universe expanded following the Big Bang, logic dictated that the gravitational attraction of all matter should pull at that expanding material and cause the expansion to slow. But how much was the universe slowing down? In the 1990s, the Hubble Space Telescope made it possible for teams of scientists to answer the question by studying the brightness of light from a special type of exploding star called a Type 1a supernova. I paid a visit to the Lawrence Berkeley National Laboratory in San Francisco and met with astrophysicist Saul Perlmutter, who headed up the Supernova Cosmology Project. So what did you find out?
So we started to make a measurement to try to find out how much the universe in its expansion is slowing down. When we first saw the data, you say, well, that's kind of funny. It kind of looks as if the universe isn't slowing down. But you assume, well, but we're also right in the midst of doing all these checks and calibrations and confirmations, and I'm sure once we get all the numbers checked out and figured out that the effect will go away, change of sign somewhere that we'll have to fix.
There's a minus sign.
Yeah,
it's
right.
supposed to be a plus,
Something as trivial as that. You check each step of the process, and little by little, you get to the point where you start realizing, this effect isn't going away. This is the right answer. It really looks like the universe is actually speeding up.
So why is this so important?
This acceleration of the universe doesn't fit at all. We understand pretty well what all the forces are in the universe and what all the objects are in the universe. And this is one of the first times that we've come across something that we wouldn't have predicted. Now we're having the fun of trying to figure out what does this all mean. And if you come with me, I'll show you a little bit about what we're doing about it.
Why is it accelerating?
Well, that's the question that has us all dying to know the answer. And I mean, one way to think about it is that if you have an energy of this odd sort that would pervade all of space, it can actually speed up the universe when gravity is trying to slow it down. And we're calling that dark energy just to reflect the fact that we don't know what it is.
It's a mystery.
It's completely mysterious, bizarre. We have no idea what it is. We want to do studies to figure out what could dark energy be like. What we want to do now is get data that will help pull apart the different answers.
So where are you going to get that data?
The big picture goal that we're after is a project that you see around you here, which is a satellite project. The design that we have here we've called SNAP, which is short for Supernova Acceleration Probe. This would be a new space telescope with a very, very big field of view. So instead of looking through a little keyhole at the universe, you'd be looking through a good picture window at the universe. So let me show you what we're working on that we think might help us get at why the universe is accelerating, what this dark energy really is. Here we have SNAP that we're hoping to be able to launch not too distant future. This one goes out to a location out past the moon. From that vantage point, you can measure the expansion history with such detail that we could actually see the little changes when it goes from deceleration to acceleration. Back when the universe was really dense and close together, gravity was more important and it slowed the expansion down. As it kept expanding, though, even slower and slower, it lost out. And gravity became less important than the dark energy, which took over and started to accelerate the expansion. And we're after exactly how that changeover occurred, and that will tell us about what different possible theories could be right to explain the dark energy.
Always expanding, but
Exactly.
slowly then speeding up.
Exactly.
And
So
that's where we are now.
Exactly. So it's this issue of did it slow down and then suddenly spurt, or did it slow down and and come to a wobble and then take off? What was that transition like?
Just like the ancient astronomers, modern scientists have discovered something about the cosmos that we cannot yet explain.